Okay, so let's wrap up section 3 with two short definitions. And the first is that of a potential. Okay, so if a vector A, a vector A is described as, a vector field A, it depends on x, y, and z, is described as potential if the curl of A equals 0. Okay, so it's potential or irrotational. Okay, we saw before, just in the last section, that the curl of the gradient of a function was identically 0. Okay, so if we compare these two things, then this tells us that A must be someone's gradient. Okay. Okay, i.e. there exists a function v, okay, that depends on x, y, and z, for which A equals the gradient of v. Okay? And v, this v, is called the potential. Okay, a second definition is that B is called solenoidal if the divergence of B equals 0. Okay, and analogously, before, in the section before, we saw that the divergence of the curl of a vector was equal to 0, identically. Okay, so this tells us that B is someone's curl. So B, so there exists an A such that B is equal to curl of A. Okay, and in this case, this is called the vector potential. Okay. So if curl A is 0, then we can write A as the gradient of some potential. And if div B is 0, then we can write B as the curl of some vector potential. But note, this vector potential A and this scalar potential V, they are not unique. Okay, because let's take the scalar case. So A equals the gradient of the potential V. Okay, what if we replace V with V plus a constant? Okay, so this V depends on x, y, and z, but this is a constant. Then A goes to the gradient of V plus V0. Okay, but the gradient of V0 is just 0. So this is the gradient of V. Okay, which is unchanged. So A remains unchanged under addition of a constant. And similarly, if we think about the vector potential, so B is given as curl A. Okay, what happens if we change A? Okay. So here there's an A whose curl gives us B. But this A is not unique, because if we add to A the gradient of some scalar function, let's call it chi, okay, then what happens is that B goes to the curl of A plus the gradient of the scalar field. Okay, and this is just two terms. This is the gradient, sorry, this is the curl of A plus curl. Okay, and this thing is 0 identically. So we get curl A back, okay, which is just B that we started with. Okay, so if there is an A, if there's a potential field, then there is a potential, but this potential is not unique. We can add constants and we still get the same A when we take the gradient. If the field is solenoidal, i.e. the divergence of the field is 0, then there exists a vector potential A, but again it's not unique because we can add the gradient of a scalar. Okay, and this is key to describing photons and light and other force carriers in nature. Okay, and this is gauge field theories. Okay, so you've probably heard about the Higgs boson. Okay, and it arises from some considerations of gauges when you're working with describing charges and particles in a system. Okay, don't worry about the physics. We're focused on the mathematics. All right, that ends section 3. So well done for getting this far. Next up is section 4, where we consider line integrals and double integrals. Okay, so we'll change our direction somewhat. All right, thanks.